Hello everyone. Since we already have a pretty full house, I think we're going to get started right on time. Thank you so much for coming. I'm Jillian Epstein, the outreach coordinator for the Cornell Astronomical Society. And thank you so much for coming to our special Carl Sagan Night lecture. I'm very excited to introduce Professor Shami Chatterjee. Professor Chatterjee is a research professor in the Department of Astronomy. He does research in radio and the search for extraterrestrial intelligence. And I will let him tell you a bit more about himself. So please welcome Professor Chatterjee.
Thank you. All right. I think standing here is causing feedback. This is okay? This is okay for everyone? Okay, great. Right. Well, thank you all for coming. This is the first of the events for what would have been Carl Sagan's 90th birthday. And there's a whole range of events tomorrow and various other things. Please look at the website for a full listing. There's a whole bunch of activities ongoing. What I'm going to talk about today is it's grandly titled, Are We Alone? The Search for Life in the Universe. And this was, of course, a topic very close to Carl Sagan's heart. But I'll start off by telling you a little bit about me. I'm a research professor, as Jillian said, at the Department of Astronomy, and I work at the Cornell Center for Astrophysics and Planetary Science. I mostly work on fast radio bursts, gravitational waves, whole bunch of different things. Last summer, we announced, for example, the discovery of low-frequency gravitational waves. We were all super excited to announce that. But that's all. Today, what I'm going to focus on, though, is one of my other lines completely. And that's to talk a little bit about how we got here and what that might mean for life elsewhere in the universe. All right? Okay, let's get started. Oh, and if you have questions or clarifications during the talk, please just stop me as we go. That's no problem at all. Or when we get to the end, I'll be happy to answer questions. Okay, let's dive right in. Where do we come from? So I'm going to start off with this picture of, maybe the light's down a little bit on that side. Yeah, thanks. I'm going to start off by showing you this picture. These are two pictures from the Hubble Space Telescope. On the left-hand side is what it looks like in visible light, and on the right hand, what it looks like in infrared. And the power of infrared light, of course, is that it's a longer wavelength, so it goes past, if you will, the dust molecules, and so you can see through the dust. And what this shows you, what this picture shows you right away, is these it goes by the name of the pillars of creation, because you're seeing these clouds of dust which are very, very cold, and these clouds of dust are collapsing. And then at the tips of the clouds, you see them glowing bluish because of newborn stars inside. And so this is our picture of how stars form, is that very, very cold clouds of gas and dust slowly collapse. Eventually, they collapse until they're gravitationally bound, and then nuclear fusion turns on inside, and they become stars. Okay, so we have these stars forming in these clouds, cold clouds. We also today understand where planets come from. And so at the ALMA Observatory, which is up on the high, dry plains of the Atacama Desert in Chile, there are these millimeter wave observatories, dishes. And these millimeter wave dishes were used to produce this picture. This is actually a real image, not an artist's conception. And what you're seeing is at the center, a protostar, a newborn star that's just beginning to turn on. And then surrounding it, this flat disk of gas and dust. And inside that disk of gas and dust, you're seeing these paths that have been carved out. And these paths have been carved out by newborn planets. So we're literally witnessing the birth of planets. You have these stars forming, protostars collapsing, the disk of gas and dust, and then inside it, newborn planets emerging, sweeping up this gas and dust, and then forming a whole planetary system. And today we have lots and lots of these images of baby planetary systems in the process of being born. And in all of this, I've mentioned gas and dust. And you might say, okay, so where's all this dust? Where's all this stuff coming from in the first place? Right? So we've talked about the birth of stars. We've talked about the birth of planets. And then when planets are particularly massive, they die in these massive supernova explosions. And so for a brief instant of time, a supernova explosion outshines all the stars in a galaxy full of stars put together. It is extraordinarily bright. It is one of the most energetic events that we know of. And what it leaves behind is this cloud of gas and dust that's exploding outwards. It's literally the explosion left behind after the supernova goes off. And so here you see a very famous supernova remnant. It's Cassiopeia A, and it's color-coded by the different elements in there. So for example, the parts that are glowing greenish are greenish because they have extra oxygen in them. The parts that are the jet-like things that are in red that are sticking off to the side, those are extremely rich in iron, and so on. So the different elements that are formed, that are cooked inside the hearts of these stars, are blown out into the medium by the death of these massive stars. And so you really have this perfect recycling process where you have stars forming, elements being synthesized inside them, stars dying, and all of this going out into the interstellar medium for the next generation of stars and planets to be born. And so Carl Sagan was fond of saying, we are made of star stuff, because all of the stuff, all of the heavier elements inside our bodies, everything other than hydrogen, was formed in the cores of these stars when they died a long time ago. So all the oxygen, all the carbon, all the nitrogen, all the sulfur, all of this is being born in these stellar explosions and then seeded into the galaxy for the next generation of stars to form. Okay, so that's basically in 3 slides, a complete picture of stellar birth, evolution, death, and obviously this is a semester-long course that we've covered in 3 slides. The thing that we want to take away from this is that none of these things that I described to you are specific to the sun or the earth. These processes are all universal, right? So you have clouds of gas and dust forming protostars, disks, older generation of stars providing the heavier elements. These could happen and do happen everywhere in our galaxy. Okay. Right. No, they do get mixed very, very well during this process of these cold, dark clouds collapsing. The collapse and the angular momentum, which causes them to swirl around, mixes them well as well. So yes, it gets mixed up. And so this brings us to the Copernican principle, where Copernicus thought about this and concluded that the Earth is not at the center of the universe. In fact, he says, the massive bulk of the Earth does indeed shrink to insignificance in comparison with the size of the heavens. And so Copernicus tells us, okay, we are not at the center of the universe. And so then you look out onto a field full of stars, and what you're seeing here is all of these stars are stars in our own galaxy, except that little smudgy thing in there. That's our nearest neighbor galaxy, that's Andromeda. And that's full of 1 billion stars as well, right? But all of the other stars are in the foreground. They're part of our own galaxy. So if Copernicus says we are not particularly special, then that brings us to what we call the Fermi paradox. And it's named after Enrico Fermi one day at lunch at Los Alamos, turning around to the other scientists having lunch there while they were building the atomic bomb, actually, and saying, well, where is everyone, right? That's actually a pretty profound question. Where is everyone? So what might be the answer to the Fermi paradox? The first answer is the pessimist answer, which is, well, we are alone in the universe, they don't exist. And to be completely upfront about it, this is still a valid answer, right? If this turns out to be true, it would be an incredibly profound statement, but we don't yet have a way of ruling out this answer. Okay, and so that's really the heart of this entire enterprise of looking for life and civilizations elsewhere, is trying to prove the pessimists wrong. And if not, if the pessimists are right, then I guess that tells us something deeply profound as well. All right, let's set that aside. We'll come back to that answer at the very end of the talk. What other answers are there? Well, there's the conspiracy theory answer. They're here. We're covering it up. And really, the whole thing with they're covering it up, it really, I think everyone now walks around with like high quality phones and video cameras in their pocket. And the evidence for these things, it does not grow at the same rate. It just does not. And so back in the days of blurry film pictures, it seemed like, wow, really, maybe there was something to it. But now everyone is constantly walking around with a camera and a video recorder, and it just is not true. All right, so we're going to set the conspiracy theory aside for the rest of this talk. And instead, there are possible answers to the Fermi paradox. Can we get rid of that little bar there? I have to get it just so. Nope. I cannot click it. All right. Sorry about that. You guys will have to live with. No, I actually am not live on Zoom anyway. Oh, well. Okay, so the Fermi paradox, one of the possible answers is that maybe, just maybe, life is commonplace in our galaxy, but intelligent life, and especially intelligent and technology using life, is very, very rare. And that would answer the Fermi paradox, because really we have, until very recently, we have had no way of knowing if there is life around other stars within our own galaxy, right? So maybe the answer to the Fermi paradox is that life is commonplace, its intelligent life is rare, and technological civilizations are extremely rare. And if that's true, well, we should investigate. So how do we go about this? This seems like an extremely general problem. It's too big to wrap our brains around. The simple thing that we might do is we might say, okay, let's start off by looking for life as we know it. Okay? Not just any general kind of life, super intelligent gas clouds talking to each other. We would have no way of figuring that stuff out. Let's look for simple things like life as we know it. And what is it that's essential to life as we know it? What is the one thing without which we definitely would not have life as we know it on the planet Earth? It's liquid water. Yeah, so liquid water really is an essential element. And so we might say, okay, where do we have liquid water? And I want to emphasize before we dive into this, that is a very, very conservative position, right? We could have many other forms of life as we don't know it. But to start with, we're going to look for life as we know it. And so we define something called the habitable zone in our solar system. And we will generalize this to other solar systems when we find them. We talk about the habitable zone, which is the zone within which liquid water might exist. And in our solar system, Mercury is obviously too hot. Venus is too hot, although it sort of could be borderline if it didn't have runaway global warming on its surface. And then Mars is too cold. And then in between, just right, is the Earth. That's a big surprise, right? I mean, this is one of the problems of this life as we know it exercise. Life as we know it necessarily tells us that we're looking for planets like our own, where we might have liquid water. But that's okay. That's not too bad. Where else in the solar system might we have liquid water? Now, I'm not actually going to talk to you. That's not so good. What has happened here? It's back. Okay, good. I will just have to try not to step on the cable. Okay. All right, technical difficulties. Let's hold on for just a second. All right. All right, sorry about that. Hopefully I'll manage to not step on this. Okay, so I won't actually be talking too much about the solar system because today I really want to get to some completely different stuff. But I'll just tell you, in our solar system, what are the top candidates for life beyond the Earth? Well, first of all, of course, is Mars. Mars, the red planet, it's fascinated people all along. We see these, what looked to people like ice caps at the poles, although today we understand they're actually they're carbon dioxide, they're not water. But Mars, at some point in its history, did have liquid water. And so today it is one of the top places that we want to investigate to look for possibly fossil evidence of life having emerged at one point in the past. What else? There are the icy moons of Jupiter. There's Europa, and then the icy moon Enceladus around Saturn. These are beyond what I just said was the habitable zone. What gives? It turns out that Europa has this icy shell, but then inside it is heated tidally because of Jupiter. The tides that Jupiter causes basically keep the inside of Europa nice and pleasant. And Europa has much, much more liquid water than the Earth does at this point. So it's a very, very interesting place. It's a very high priority for missions. And of course, recently we just launched a spacecraft to try to visit Europa and investigate. Enceladus, similarly, is a moon of Saturn, and it has a vast amount of liquid water underneath it. And in fact, the Cassini mission to Enceladus, Cassini mission to Saturn, when it flew by Enceladus, found these plumes of liquid water because of liquid water volcanoes erupting from the surface. And so all you really have to do is potentially fly through those plumes and you can look at what's under the oceans of Enceladus. Very, very interesting. And then the last interesting candidate site in our solar system is Titan. This is not life as we know it. It's the only moon which has an atmosphere. And it's a hydrocarbon planet. So the chemistry on here would not be life like us. It would not be water-based. It would be some kind of chemistry with ethane and methane. Could that be life? We have no idea, right? We have just not even begun to investigate these possibilities. Okay, let's move on from our solar system. As I said, this is its own talk. But what I really want to talk about is beyond our solar system. So till the 1990s, we had 9 planets in the solar system, and then we had 8. But in 1992, we found the first planets beyond our solar system, right? These are extrasolar planets. The first ones that we found were actually exotic. They were found around a neutron star, the kind that I like to study. But since then, we have today found over 5,000 planets beyond our solar system. We know lots and lots of planets beyond our solar system. And in fact, the key to this revolution was the Kepler mission. And here I show you Kepler with the bunny-suited technicians setting it up before it was launched. So it's a telescope that looks like this. And the idea behind Kepler was very, very, very simple. Okay, the simple idea is this. They wanted to look at a star. Here's a picture of our sun. And they wanted to see planets crossing in front of it. Okay. Do you see a planet in this set of pictures of the sun? If you look closely, you'll see Mercury crossing in front. Sorry, not Mercury, Venus crossing in front, right? You can see it just blipping across the upper half of the sun. With Kepler, though, you are not going to be able to resolve the disk of a star. What you're going to do is you're going to measure how much light is coming from the star to extraordinary precision. And then you're going to look for it to dim by the amount that is blocked by a planet crossing the face of the star. Okay, so the amount of light that Venus has blocked off here compared to the rest of the brightness of the sun. That's the change in brightness that you're going to measure. And of course, this sounded like a completely crazy idea. People laughed it off. NASA rejected the proposal multiple times. Eventually, they flew it. Okay? And the idea behind the Kepler mission was purely statistics. They were not looking for specific kinds of planets. They were not looking for habitable planets. They just wanted to answer one simple question. They were going to stare at one patch of stars in the sky. So these squares there are the detectors on Kepler. They were going to look at that one little patch, monitor all the stars in that patch very, very carefully, and say how many of the stars in this patch have planets around them, which are aligned edge on so that the planets pass between us and the star. The planetary system could be tilted and then Kepler would not see it. But that's an easy geometric effect. You can just correct for that after the fact. So they just wanted to look for edge-on planets. How many stars in this patch have edge-on planets? Okay, that was a primary goal, was statistics. And you know, when they launched it, they were like, okay, so we probably have to look for a couple of years and then do the analysis. And then maybe if we're very lucky, we'll find that one or two of the few thousand stars in here have planets, because we had no idea how common planets are. And it's really, really hard to grasp what happened, because as soon as they started getting the data back, they started finding planets, and they started finding planets with orbits which were 3 days, 3.5 days, 3.2 days, 4.9 days, 3.5 days. These are planets that are going around their stars in less than a week. What they thought was going to take years to get evidence for planets orbiting these stars, planets were everywhere. As soon as they turned on the detectors, they started seeing these dips. And you can look at these dips and you can say, okay, that's not like a solar flare or a star spot or anything. There's a very characteristic U shape which says this is a planet passing in front of the star. Okay, this was just a complete transformation of our expectations when Kepler turned on. And then now, again, I'm showing you the detector plane of Kepler, and every colored dot there is a star there with planets around it. And remember, it's not just planets, it's planets that are edge on, specifically edge on, so that we can see them. Okay, they are everywhere. And they're in astonishing variety and diversity, just what Kepler found. It found planets that were Earth size, the blue dots. It found super Earth size, 1.5 to 2 times the size of the Earth. It found Neptune-sized planets. It found Jupiter-sized planets, all of them. Right? There were vast numbers of planets. And not just planets. Kepler found planetary systems, right? So here, for example, there are a few of these. There's Kepler 186, there's Kepler 452. These planets were inside the habitable zone of their host stars. If they have water on their surface, they have liquid water. It's not ice, it's not steam. These will be inside the habitable zone of their respective stars. Okay, so the follow-up to this was the TESS mission, which is basically to look now, not for statistics, but for juicy planets that are nearby. And TESS was launched in April 2018. That survey is ongoing. This is the first light image from TESS, basically. And TESS is basically looking at these stars, looking for planets to cross in front of them, and looking to see, okay, can we find planets, right? Truly extraordinary. But let's say now we've answered the first question that we had when we started to say we should look for life as we know it. We are trying to look for planets. We found planets. We're trying to look for planets that might have liquid water. We found plenty of those now. Okay. can we now actually look at those planets and try to get evidence for life? How would we do that? Well, let's turn the problem around and say, okay, imagine an alien astronomer who looks with their telescope at our solar system. Can they tell that there's life on Earth? Is it possible? Is it easy for them to tell that there's life on Earth? The first thing that we want to do if we can get light from something is we want to expect from. Basically, it's like you take the light from the sun and you put it through a prism and it breaks up into a rainbow. Except if it's not white light, it won't break up into a uniform rainbow. It will break up with, there will be dips and extra emission and absorption, and that will tell us something about what's in the source that we're looking at. If you take the spectra of the planets in our solar system, these are 3 example spectra. The upper one is Venus, the middle one is the Earth, the lower one is Mars. And just looking at it without knowing anything else, you can say one of these is not like the other 2. Right? Without knowing anything else, you can say that right away. The big dips are carbon dioxide. All of these planets apparently have carbon dioxide. Okay, that's not very exciting. But the Earth has dips associated with water and with ozone. Now, ozone, of course, is incredibly reactive. It will immediately react with elements and go away. What does the existence of ozone tell you about the Earth? It tells you that the Earth is not in chemical equilibrium because something is pumping free oxygen into the atmosphere. And what is that? It's plants, it's life. Just looking at these spectra, you can tell that there is something on the Earth which is out of chemical equilibrium. And the most plausible explanation for that is that there is life on Earth. Okay, so that's very exciting. Maybe we can do that. The problem, of course, is that it is very hard to get a spectrum against the glare of the star. Because remember, you're looking at the star and you have these planets which are right up next to it. The stars shine, the planets don't have light of their own. They shine by reflected light. So not only do you have to get rid of the light of the star, you're looking for a very, very, very faint signal, basically. So that turns out to be a hard problem. And again, since this is specifically to Carl Sagan's 90th birthday, I want to show you one of the papers that he worked on. It's a search for life on Earth from the Galileo spacecraft. And it's a cute little idea, which is you take the Galileo spacecraft and you train its cameras on Earth. And you say, could we tell that there's life on Earth? And the answer, of course, is yes, you could tell that there's life on Earth. And it's not just what I showed you. There's also, from the Galileo spectrum, there's methane, there's the edge of, there's a red edge corresponding to vegetation on Earth. You can do a lot if you can fly a spacecraft next to your exoplanet. We are not going to fly a spacecraft around a planet beyond our solar system anytime soon, right? Our spacecraft have only just left the solar system for the first time fairly recently. And that's the Voyager probes have now just crossed the boundary of our solar system. Getting to the next star even is many decades away. So what can we do? Well, maybe we can be very, very clever. We can maybe use something called a coronagraph. And what a coronagraph is something that you can position on an image so that it blocks the light of a star while allowing the light of a planet next to the star to shine through. And the James Webb Space Telescope, for example, has these 2 coronagraphs. It's not just as simple as that. It's not just that it's like a big disk that you use to block it off. The techniques for doing this get to be very, very fancy because light doesn't just travel in straight lines, it also diffracts. And there's lots of spillover light and reflections and so on. But on the James Webb Space Telescope right now, there is this coronagraph. There are a pair of these coronagraphs. And so with JWST, you can get images that look like this now, where it's showing you that bright star, HIP 65426, just a catalog number. The lower images, the little white star is where that star would have been. The light of the star has been completely blocked off by the coronagraph. And instead, what you're seeing is a planet that is orbiting that star. So we've used the coronagraph to block the light of the star. We can now see the planet next to it. This is incredibly, incredibly difficult, and it's only just become possible. You can see that the images of the planet look, they have lots of artifacts. It's not like a disk. We're not going to see continents and clouds or anything like that anytime soon. But what we can do now is take spectra of these planets, and we can start looking for non-equilibrium chemistry. And therefore, we can start looking for evidence of life, right? Eventually, the goal is to be able to take spectra of planets in the habitable zones of their stars and say, okay, is there something here or not? This is literally like hot off the presses kind of a thing. This is ongoing work. Eventually, someday, we might be able to fly star shades where we have a telescope and then a star shade flying a few tens of thousands of kilometers away from it, but in formation so that it blocks off the light of the star and lets you look at the planet. These are basically drawing board concepts that people have talked about someday. Formation flying to block off stars to extreme depth. But that's pretty far away. So far, what we have is we have started to get spectra of planets beyond our solar system so that we might be able to find evidence of life. But what if we don't just care about life? What if, okay, fine, planets have algae and bacteria? That's profound. Don't get me wrong. That's completely profound that there's life elsewhere. But that's not very interesting in terms of, exchanging Wikipedia or anything like that. That's not very, what we're really interested in is intelligent civilizations. So how do we look for that? The idea for this, the search for intelligent technological civilizations, how to search for it, it dates back a long time. But one of the pioneers in this enterprise was Frank Drake, who was an astronomer here at Cornell as well. And he started something called Project Ozma. He named it after the land of Oz, which is very far away, difficult to reach, and populated by strange and exotic beings. So he called his search Project Ozma. And he basically pointed a radio telescope at some nearby stars, looking for radio transmissions. Because his reasoning was, if there are intelligent technological civilizations around these other stars, they will probably invent radio, because radio is a very useful way to communicate or signal or whatever else. And so he wanted to search these stars for radio emission corresponding to civilization. At what frequency should you look? There's a huge range of radio frequencies. He said, well, okay, anyone who's a radio astronomer knows that hydrogen is the most common element in the universe, and hydrogen has a very specific radio emission frequency of 1420 megahertz. And so if you want to be found by other people, other civilizations, you would say, where would an alien astronomer look? Probably at 1420 megahertz. So we should transmit there. And so you can see the circular logic a little bit, but he started off with a survey at 1420 megahertz. And he found nothing, but it was proof of concept. He only had a chance to look at a couple of stars. This whole thing with radio surveys, finding things of interest, goes back a long way. So this is Jocelyn Bell standing in front of her radio telescope. The young people in the audience will not recognize this as a telescope. But if you're older, you might recognize things that look like old TV dipole antennas. That's basically what her telescope was. It was basically a field full of these dipole antennas. And she was starting up to look for something else altogether. But her telescope produced these miles of chart recordings. And in those chart recordings, there were these little squiggles, which were interference. And then there was this other little squiggle, which she figured out was actually coming from the sky. And they named it LGM1, because they were like, little green men one, joking, maybe not joking. But then very quickly they found LGM2 and LGM3, and we now know these as radio pulsars, which is what I primarily study. They have nothing to do with alien civilizations. They are purely natural phenomena. One of the most famous false alarms, again, maybe, in this enterprise goes by the name of the wow signal. This is basically Jerry Emmon at Ohio State was doing a survey with what they call the Big Ear Telescope. Again, this is primitive stuff back then. So the chart recorder basically wrote 0, and they didn't even bother writing 0, or 1 or 2 or 3 if it was noise, right? And you can see that it's basically 0s, 1s, 2s, a few 3s, and then suddenly in this one narrow channel, there's a signal, and the signal is bright. It goes 5JUQE6. Enormously bright signal in a very narrow channel. He saw this on the recording. He circled it with a red pen and wrote wow, became famous as the wow signal, never seen again, right? Could it have been a transmission directed towards us? Could it have been something else altogether? Right now, our best understanding is that this is not, in fact, ET. It's something, anyway, it's a fairly technical possibility of what it could be. But it could have been. We wouldn't know. Another natural phenomena that started off as looking potentially interesting, there are these fast radio bursts. Again, that's something that I study. These are coming from distant galaxies, and there's tens of thousands of these popping off every single day all over the sky, just brief flashes of radio waves. Very bright, very energetic, coming from very, very far away. Typically, we don't yet understand what they are, but we do understand that they are natural phenomena. They're not aliens. Okay, so I've covered all of this as things that have come up as candidates. It turned out SETI basically became a not so respectable field of study for a while there, because some senator got up in Congress and said, oh, they're wasting taxpayer money to look for little green men. And that was really the end of that. So all of our public funding for SETI dried up. Right now, though, we have, this is a picture of Stephen Hawking with Yuri Milner, who was a Russian billionaire. And he decided to put a whole bunch of his Russian billions into SETI. And so he funded this program called Breakthrough Listen, which is a program to do SETI observations. They literally buy time at the Green Bank telescope, and then they look for SETI signals. And, and they're very collaborative. We collaborate with them on scientific projects. And they're looking for, we use them to study pulsars and everything else, but they also are looking for possible signals. And then have some of you seen chatter about VLC1? Some of you have possibly seen chatter about it? Okay, no. This was a little boomlet that happened fairly recently about, oh, and Breakthrough Listen has found aliens. What was that about? Let me just tell you briefly what it was about. So Breakthrough Listen buys time at the Green Bank telescope in West Virginia, and they buy time in Australia at the Parkes telescope. And in some observations taken at the Parkes telescope, they found this signal. So what you're seeing here in these green things is frequency is on the lower axis. So think of that as tuning the dial of the radio, and then time marches up across, marches down across the page. So early times, later times. And you can see a narrow signal in there. Let's zoom in on that one. So this is this narrow signal that was seen, and it's very, very interesting. It's narrow. It's only seen when they pointed towards the star they were looking at, and when they pointed away from the star, it was not seen. It drifts slowly in frequency. Why is that interesting? Because the idea was, if it is an alien transmission and it's coming from a planet, maybe the planet is going around the star. And so the signal will drift back and forth because of the Doppler effect. And it persisted for a few hours, but then it went away. So this is all very interesting. If it's narrow band, we know that it's probably technological. because nothing in nature produces signals that are that tight in frequency. Natural signals have some kind of spread typically. It's only seen when it's pointed at the star. That means it's coming from the sky. It's not something that's interference. It drifts, which means it's not rotating with the Earth. And it's not a satellite because it persisted for a few hours, whereas a satellite passing overhead would go through in minutes at most. So, have we detected ET? Is BLC1 ET? They've now taken a detailed look at it, and this is from the paper. An electronically drifting intermodulation product, local time-varying interference. Very, very sad conclusion that it's interference, just like most of the signals are. How can they be sure that it's interference? Well, this is why. Once they knew that this is the sort of signal they were looking for, a narrow drifting signal, they went back to their data and they said, okay, let's look for other instances of a similar signal, which are not confined to one spot in the sky. And they found hundreds of similar signals, right? They found many, many of these signals. So it turns out that this kind of signal is actually commonplace in the park's radio environment. And it's just that in this one instance, it was restricted to when it was pointing towards the star, it was seen, and when they were off the star, it was not seen. And that's just, if you roll the dice a few thousand times, once in a while, you'll get lucky. So this is basically statistics working against us. But as you can see, they've now found many more instances of signals like this. So we understand that this was not, in fact, an artificial signal. Well, I take that back. It is an artificial signal, but it's coming from the Earth. It's not coming from aliens. And so in that sense, this is another reminder that skepticism is essential in this business. Again, this was one of Carl Sagan's sayings that extraordinary claims require extraordinary evidence. And this falls very, very, very far short of that. Okay, so before I wind up, I want to tell you a couple of other things. Since this is, again, Carl Sagan's 90th, I want to tell you about one of the last papers that he worked on with people I work very closely with. And that has to do with scintillation and scattering. So you all know that stars twinkle. Okay? Stars twinkle, planets don't. And that's because planets are nearby and their disk is resolved. Stars twinkle because they're far away, they're not resolved. And as the waves as the rays of light from a star pass through the interstellar medium, they have multi-path propagation, right? So they bend away, they bend towards us. And then depending on where our detector is, sometimes it gets brighter, sometimes it gets fainter. And that's the twinkling of a star. The same thing happens at radio wavelengths. And so at radio wavelengths, for example, if we were to look at a pulsar, which twinkles, this is what the spectrum looks like. You can see the bright patches and the dark patches. That's just the signal getting brighter and dimmer, brighter and dimmer. The important thing to understand here is that that does not mean that there's more energy. It's just that there's energy that's sometimes focused towards us and sometimes focused away from us. It's the same amount of energy, just distributed differently. And so Carl worked with Jim Cordes here at Cornell and Joe Lazio, who was a graduate student here at Cornell. And they came up with this idea, scintillation-induced intermittency in SETI. And what that says is basically that some of the time when you're looking for an alien transmitter, you might get lucky. It might twinkle in a way that it just is brightened towards you. And so glass half full, you might be able to see a transmitter that you couldn't otherwise see. Glass half empty, most of the time it's not going to be brightened. In fact, it's going to be a little bit fainter, and so you will never see it again. So they worked through the numbers and they concluded that it might make an initial detection possible, but if it made the initial detection possible, it would make it impossible to confirm because it would not be bright again in a human lifetime. So this is really very much good news, bad news. Okay. Right. So where do we stand? No talk like this is complete without the Drake equation. And this is my picture of the Drake equation on a plaque on the door at Green Bank Observatory. And what the Drake equation says is, it is not an equation that tells you how many aliens there are. It's very, very important to understand this about the Drake equation. The Drake equation is basically a way of quantifying what we know and what we don't know. It's a way of quantifying our ignorance, if you will. And what the Drake equation says is the number of technological civilizations in our galaxy today depends on, up here there's a rate, which is numbers per year. And then at the end of it, there's a factor, which is years. Numbers per year multiplied by years gives you basically a number, okay? And the way this equation is working is it's a way of saying how many cars are on I-80 right now. Well, I'll monitor all the on-ramps and all the off-ramps, and I'll see how many cars are getting on per second. And I'll say, how long do the cars stay on the interstate on average? Right? So if we have 10 cars getting on every hour, and if we know that the cars spend on average an hour on the interstate, then 10 cars per hour multiplied by 1 hour says there's 10 cars on the interstate right now. Scale them up to the right numbers, right? So it's a rate multiplied by a time, and that gives you a number. That's the secret of the Drake equation. Okay, so what are the factors in this? The number of technological civilizations depends on the rate at which stars are born. We understand that very, very, very well. Okay, multiplied by the fraction of those stars that have planets. Thanks to what I showed you with Kepler, we know this answer now. We know that, in fact, most stars have planets. Certainly more than 50% of stars have planets around them. So we know this factor. The number of those planets that are Earth-like, that's a tougher number, but again, thanks to Kepler and now with TESS, we are answering that question. And it's not that uncommon. Okay, so now we've done astrophysics, we've done planetary science, now we get to the tricky ones. What fraction of those Earth-like planets have life? We have no idea because we don't understand biology well enough. We don't understand where life came from on Earth in the first place. So that's uncertain. If you're very optimistic, you will say, oh, wherever there's chemistry, there's life. If you're very pessimistic, you will say life is unique on the Earth. And that determines what answer you're going to get from this Drake equation. But let's move on. That at least someday we will know this. Once we find life elsewhere, we will know what this factor is. But then what fraction of that life becomes intelligent? That's really, really hard to guess at. And then what fraction of that intelligent life develops a civilization that's technological? Who knows? And then finally, the time, and that time is how long that technological civilization lasts. And now we're into sociology, and you know that there's nothing harder than that. And that's just not going to be something we can answer anytime soon. So the biggest unknown in the Drake equation really is the lifespan of an intelligent technological civilization. All the other factors we could at least see routes to answering, but L is very, very hard to answer. And that has led to this idea of the great filter. The great filter says any intelligent and technological civilization encounters something that kills them off, okay? And if it does, that would explain the Fermi paradox, right? You look up at the night sky, there are all these stars, there are all these planets, we don't see intelligent technological civilizations around them. There don't we? Because of the great filter. Now that's an incredibly scary answer. And the big question that comes up immediately is if there is a great filter, is it in our past? For example, we know that humans came very, very close to total extinction in the fairly recent past. So 70,000 years ago, roughly, there was the Toba supervolcano that went off. It created a global cloud of dust, global winter. The human existence was down to approximately 70,000 individuals. So that's a bottleneck in human history from which we have recovered. Was that the great filter? If so, that's great news, because that means we're past it and we can go ahead and we have the galaxy open in front of us. The alternative is that the great filter is in our future, and that any intelligent technological civilization basically ends up degrading their environment to the extent that, well, they don't get very far off their home planet. We don't know which one of these is the right answer. You can look at this graph. This is current to a couple of days ago now. Not looking good for us right now with the great filter, but here we are. Okay. Let's do one last thing, which is, what about alien astronomers? If they have turned around to look at us, have they been able to see us? Well, there was one occasion, one famous occasion, where we beamed a message from Arecibo Observatory in 1974, and it was beamed towards M13, which is 25,000 light years away. It's a globular cluster. So it's got hundreds of stars, but it's 25,000 light years away, which means that it will get there in about 24,900 and something years from now, right? It's not gotten very far yet. But that message basically had 1,679 bits of information. And if you are a mathematician and you think about that, you go, oh, a product of two prime numbers. I wonder if I can arrange it. And if you arrange it in a 73 by 23 grid, you get gibberish. But if you arrange it the other way in a 23 by 73 grid, you get this. And this, if you squint, you can see a picture of a human. You can see a picture of the double helix. You can see pictures of the transmitting Arecibo telescope. You can see the sun and the third planet from there, from where this signal is originating. There's all of this information. None of this is meant to be taken seriously. This is purely an exercise in saying, if we were to send out a transmission, what might we want to say? But here's the really sad thing. We've done this once. Let's say it just so happens that it passed over a planet that was relatively nearby, that had a curious astronomer who was looking at us right then. They would find that signal and they would write down on their chart recording 6JQUE, and then it would never recur again. It would be just like the wow signal, right? We've only done this once. So just to get a sense of the scale of things, what about leakage radio transmission? So we've been transmitting pretty strong radio signals since the 1950s. Although with the advent of cable TV and so on, there's been less of that. But still, we have airport radars, we have military radars. These are bright radio beacons. How far in the galaxy have we managed to transmit our presence since the 1950s? So 1950s, that's about 75 years, which means radio waves have traveled a sphere of 75 light years in radius. On the disk of the galaxy, if you zoom into this bit, that little blue circle is how much of the galaxy we have made aware of our presence. That's the scale mismatch we're talking about, right? And so to go back to the Fermi paradox, where is everyone? One of the things Carl Sagan was fond of saying was, well, they're just about to get here. Because really, we've only just begun to set foot in the wider galaxy around us. Okay, so like I say, we've hardly made a dent here. What we have for now is basically this. I have to leave you with this image. It's contractually required. What you're seeing here is, this is basically the very, very famous pale blue dot. When Voyager 1 was had finished its primary mission on Valentine's Day in 1990, it turned around and imaged all of the planets in the solar system. And this is the Voyager image of the Earth. And so Carl Sagan writes about that. Consider again that dot. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. So there's perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. And I'll leave you with that. Thank you very much.
Thank you. Wow, we have a full house here. If anyone has any questions, feel free to raise your hand. If anyone on Zoom has any questions, feel free to type them in the chat. So anybody, I open the floor. Go for it.
Yes. Yes. Yeah, so just to repeat that, it's the idea behind the Fermi paradox. Where is everyone? Well, what if there's lots and lots of alien civilizations, but they're all small? They're, in fact, let's suppose they're all comparable to us, and we've barely set foot in the galaxy, right? This is how far in the entire galaxy we've gone, and our spacecraft have only just, the first spacecraft has just left our solar system, let alone got to the next nearest star. How would we expect to know other technological civilizations? That's right. The argument against that was, it's not necessarily a good argument, but the argument against that goes back to the Copernican principle, that we are unlikely to be the most advanced civilization in the galaxy. And so if there are much more advanced civilizations, and if they've gotten past the great filter that they might have faced, then they should be spreading out in the galaxy and there should be evidence of their technology. Now, there's many things wrong with that argument. First of all, there's this, that's where the fear of the great filter comes from, is that why don't we see such civilizations? Well, that means they must have died off. Or there are intelligent technological civilizations that have just not chosen to colonize the galaxy. Or one of the answers that, again, Carl Sagan was fond of, was that I showed you at the beginning that it requires many generations of these stars to form, die, explode, enrich the interstellar medium before you end up with enough chemical complexity for life to emerge. So what if we're not the first, but we might be in the first wave of civilizations that are beginning to investigate the galaxy? Just because it's taken a few billion years since the birth of the universe for there to be enough chemistry to allow for complex life to emerge. And then that's the answer. That's how far in the galaxy we've managed to set foot in. And for all we know, there's little dots like that all over the place, and they're all branching out at roughly the same time. And then eventually then we will meet if we get past our great filter. Yeah. Okay, that's a really interesting idea. Is if other alien astronomers are using the same transit method to look for the Earth, there are other methods that they might be using. But if they are, you can ask the question, which other stars would be aware of our presence using transits in front of the sun? And then yes, that would be in the plane of the ecliptic, in the plane of the sun and the Earth. Would be, but there's plenty of stars there. There's literally millions of stars still. No, because there might be others that are much nearer to us, right, in all directions. And they might be using other methods to find us. There's many other, I talked to you about transits just because that is by far right now the most productive method, but there's many other methods that we also use to find planets, and they don't have this edge-on bias. So, yeah. Oh, yes, sure. Oh, okay. Is the money from this a defense project? No, not at all. Um, the search, trying to understand the origin of life and how it emerges that's pure science. That's funded almost entirely by NASA and the NSF. The SETI aspect, as I said, it used to have public funding, and now there's no public funding for SETI. The SETI aspect is purely privately funded, which I personally really, I mean, I think that that's enormously annoying, because anyway, that's a different argument. But yeah, the funding basically for the astrobiology part and for how life emerged, that's all science funding. Eventually, if we do find something, then I'm sure defense will be very interested. But until then, no, it's very low on their list of priorities. Okay. Is there a way to use Yeah, is there a way to use AI in this search, to expedite this search? So yes, I don't know about AI per se, but we do use machine learning methods for example, for the search that I showed you with BLC1, we use machine learning routinely on those big data sets because we're talking about many, many, many terabytes of data that have to be searched for very specific signals. It's like, the analogy we like to use is it's not looking for a needle in a haystack, it's looking for a needle in a haystack that's full of other needles. And as it turns out, we found one needle, but it turned out that it was actually one of the false positives. So yeah, machine learning methods are used for that sort of thing. Do I think we'll get past our great filter? Specifically this week, I'm going to take the fifth on that.
Okay, if we don't have any other questions, let's give one more round of applause to Professor Chatterjee. Oh, sorry, you're good. Thank you so much to everybody for coming. What a great way to kick off a celebration of Carl Sagan's 90th birthday. If any of you are interested in the events happening for the rest of the weekend, follow this website. As always, the Fuertes Observatory will be open for tours and stargazing depending on cloud cover. From 8 to 11 tonight, notice the slightly earlier end time, but we will also be open from 10 p.m. to midnight tomorrow to kind of bookend this celebration. If anyone has not gotten one of our awesome SETI Carl Sagan stickers, they will be on this table. I don't know how many I'm holding right here, so I hope everyone gets a chance to get one. Thank you again so much for coming, and have a great rest of your night and weekend.